I'm sorry, did you want one? We are at the last in our series on counting, combinations without repetition. And at this point, most of the things that we've developed, the expressions we've developed, have been pretty straightforward. But for some people, this last one, combinations with repetitions, is kind of hard to wrap your mind around. But we've got a model that hopefully will solve that problem for us. Let's talk about what we've done up to this point. Remember, we've got a set size of n. And that's basically the set that we're pulling our elements from in order to create our sequence or our subset. And R is equal to the size of the subset, otherwise the length of the sequence. Now, what have we done up to this point? Well, remember, if we were to have, let's say, ordered, right, with repetition. Now, ordered with repetition said that I can, every time I pick an element in our series, and whenever we're looking at ordered, we're talking about a sequence, right? So anytime we pick an element from our sequence, we've got n options to pick from. So it becomes n times n times n times n, r times, and that gives us n to the r. Now, if we did ordered, but without repetition, we had this thing NPR, these permutations. And there was an expression that we had for this. And if you think about it, if we had a full sequence, if we just basically were going to order our sequence from all n elements, we'd have n to choose from for the first digit, n minus 1 to choose from for the second digit, n minus 2 to choose from, and so forth. That ends up being n factorial. But not all sequences are going to be pulled from not all sequences that are pulled from this set size of n are going to be of length n. And remember, we also talked about how n minus 1 also did the same, n factorial solution. But if we have a sequence that is at least 2 shorter than the number of elements in our set size, then we divide by n minus r in order to pull out all the options that were left over, in order to give us every possible sequence from the elements that were not picked for the first r elements. So there are our first two permutations, and sometimes you'll see this exponentiation or multiplication principle. Now, any order we started with the last lesson. So we have any order, but without repetitions. Remember, we're going to do any order with repetitions for this one. Now, any order without repetition is also referred to as combinations. And so you had this expression NCR, and what you did was you took the permutations, and then from the R elements, you divided out any possible ordering you could have for those R elements, and that would give us the total number of any order combinations. So that gave us n factorial divided by n minus r factorial, just like the permutations. But then we also divided by r factorial in order to make it so that they didn't have to rely on any sort of an order. Now, let's assume that I have 3 coins. I'm just going to throw them out on the table, and they're going to come up with some combination of heads and tails. And maybe my coins will just say A, B, and C. There are how many possible ways that they could come up? Well, n, our set, is actually equal to 2. It's either heads or it's tails. So the set we're pulling from is either heads or tails. Now, since we can have repetitions, I can actually have more than 2 different elements in the sequence that I'm putting together. Now, how many times am I going to be picking from this set of 2? Well, r is going to be equal to 3. Now, if you remember, whenever we figured out combinations, we started out by saying how many possible permutations do we have, and then can we pull out order by dividing by r factorial in order to make it so that any of the manifested orders could be divided out. Let's see if the same thing works for this. Any combination, or excuse me, if we have an order, a specific order, but we can repeat, then we had that n to the r. So 2 to the 3. 2 to the 3 gives us 8. Let's go ahead and list these out. So I could have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Wow, Is that all of them? I hope so. So the idea is there is every possible combination or in an ordered set with order with repetitions allowed, right? So I should be able to just divide out the ways these can be ordered, right? And so it should be something like n to the r divided by r factorial, which would give us 2 to the 3 divided by, and what do I have, 3 factorial? That would give us 8 divided by 6, which gives us 1 1/3. Don't think that's going to work. This is not an option. This will not work for us. So we've got to come up with some other way to represent these combinations. Now, what number are we looking for? What target number are we looking for? Well, let's take a look at our list and see what are duplicates, okay? The heads, 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 that one, there's no other one that's a heads, 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 just like tails, tails, tails. There's no tails, tails, tails. Here's 2 heads and a tail. Where else is another 2? There's 2 heads and a tail, so that one can't be used. This one says 2 heads and a tail. That can't be used. Is there any other one? I don't see one. Now here's 2 tails and a head, so we need to count that one, but we need to cross out any other 2 tails and a heads. So what we're looking for is actually an answer of 4. Now, I'm not saying that this is a proof as to how the solution we come up with, if it works, if we simply apply it to this and get 4, but I'm just showing you the target number that we're looking for here is 4. So let's try modeling this. I am going to make a bucket to hold the tails and a bucket to hold the heads. Just go with me here. And let's say that I've got my 3 rolls, all right? Or my 3 tosses of the coin. Now, if you see these 3 tosses of the coin, I could move them all the way over here so that all 3 tosses are tails, or I could move them all the way over here so that all 3 tosses are heads, or I could have it somewhere in the middle, like here, which is 1 tail, 2 heads, or I could move it over 1 position this way and have 2 tails and 1 head. Now, another way of representing this or modeling this would be to say I've got the 3 tosses, all right, and then a divider, some sort of a divider that separates which group it's going into. Is it going into the tails group? Is it going into the heads group? So right now, it would look like that, all right? So I've got 1 tails and 2 heads. If I moved this so that it was over here, I would have 3 tails, no heads. So this divider basically shows me where the partition is between our heads and our tails. Let's try drawing this a slightly different way, and a way that will give us the ability to model all 4 options. So I could have the divider and then x, x, x. I could have, and that would be 3 heads, right? I could have a tail and 2 heads. I could have 2 tails and 1 head, or I could have 3 tails and no heads. And those are all of our options, right? Well, what is this actually? If you look at this, picture a slightly different way of viewing this diagram here. Picture this divider as being an empty slot out of 4 slots. So I have 3 options. Those 3 options are my tosses, and I have 4 places where I could put those options. Excuse me, I'm going to try that again. I've got 3 items to place and 4 places to put it. So I've got 4 slots, and I just so happen to put the 3 items or 3 elements in these last 3 slots. Only 1 element can hit each one of those slots. So 4 places to put something, 3 somethings to put. How many different ways can I do that? Well, that sounds an awful lot like I have 4 places to put something, and I'm choosing 3. The order in which I choose them doesn't matter. I could pick this one first, then this one and this one, or this one, this one, this one. The order doesn't matter. I've got 4 places to put something and 3 somethings to put. So this ends up being what? 4 factorial, right? Divided by, well, 3 factorial is the number of, is r, right? And then 4 minus 3 factorial. So this becomes 4 factorial divided by 3 factorial times 1 factorial, which is equal to 4. So this is 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 1. That's just equal to 4. That is our answer. Now, let's talk about this in a little bit more, I don't know, mathematical way. So what I'm looking at is I've got a bunch of spaces to put elements. So in this case, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be our tosses, our coin tosses. And then what I need is to have dividers or spaces that are going to divide these up. So let's just so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I've got is R is equal to 9. And let's say N is equal to 4. Well, N is equal to 4 means that I'm going to have things grouped together in 4 spaces. And in between each of these spaces, so I'll have all like items here, all like items here, all like items here, and all like items here. Let's just pick colors, okay? Let's say it's red, green, blue, purple. All right, all my reds are going to be on this side, separated by a divider, and then I'm going to have all my greens, and then I'm going to have all my blues, and I'm going to have all my purples. Each one of them is separated by some sort of a divider. And these are where these spaces, these little slots, are going to be filled up. Now, each one of these is going to manifest itself as an empty spot in our selected rows. So I've got what? 1, 2, 3 empty spots. So I'm going to add 1, 2, 3 here. And so remember, I had 9, so I could go 1, 2, space, 1, or 3, 4, 5, 6, 7, space, space, 8, 9. So R is 9. I'm picking 9. They can be any element. Remember, N is 4, so I could have red, green, no blues, and then 2 purples, all right? So the way this works is that these X's could be anything from N, and I could slot them into whichever space I want. The ones that are of the same type, I'm going to group together and separate from the next type with a space, and then separate from the next type with a space. And if you look at my patterns here, I've got 2 from the first element of N. I've got 5 from the next element of N. I've got 0 from the third element of N, and I've got 2 from the last element of N. And why this works is because you can come up with any combination as long as I have blank spaces in between in order to define my groups. I should, with the repetition, I should be able to partition or come up with a unique pattern that represents that allocation of N to 9. Now, some of you may be looking at this and saying, no, this is not quite right. I'm sure that there is something that won't work. Well, let's go ahead and come up with some. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our 9. And then we need 3 spaces. 1, 2, 3. All right. What if the first element of N, we don't pick any? So there's none of them picked. So we actually have a space, a divider. And then the next element of N, we pick 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. All right. I've got one more to pick. I've got a space. I'll pick that one. Actually, no, I won't pick that one. I'll put another space, and then I'll pick the last one in the last tub. So of the 4 elements for N, none were picked for the first one, 8 were picked for the second one, none were picked for the third one, 1 was picked for the fourth one, all right? There is no way that you can't figure out an allocation of 4 elements of N to 9 without leaving at least 3 spaces in here, because remember, I have exactly 3 more spaces, the spaces for these 3 dividers, in this sequence right here. So what this is saying is, if I take, and how many spacers do I need? Well, I need, or dividers, so the number of dividers equals N minus 1, right? So I had those 4 buckets, I needed 3 spaces to divide them off. So I am selecting R from, well, how many slots did I have? I had R slots, right? But I had to add the dividers too. So that's plus N minus 1. And the expression for this is just simply r plus n minus 1 combinations. We're going to select r. Let's go ahead and apply this to some other applications, see if we're going to get this right. By the way, real quick, and we didn't talk about this too much in the last lesson, when it comes to combinations, there are a couple of representations. We could do C, N, comma, R. We've talked about this. Permutations had the same one. And then we also had N, C, R. And then also we could have this weird representation with these large parentheses. So you put large parentheses around an N over R. So these are the different ways that we can represent combinations. So let's say that I am rolling 3 four-sided dice. All right. So I've got these 3 dice here. These 3 four-sided dice. And I'm going to roll them, and what I want to figure out is how many ways could it possibly come up every time I roll it. Now it's going to take me a while to get through all of them, perhaps forever, before I can come up with every possible roll here. So I'm going to use combinatorics in order to figure out what the answer is. So what is n? Well, remember, n is the number of elements from our set. How many different ways how many different elements can we pull from a set in order to create our sequence? And in this case, it is 4, right? We've got the 4 different numbers on our four-sided dice. What about r? r in this case is equal to 3, because what we're doing is we're going to try and place these four-sided values into 3 slots. So what I've got are the 3 slots for r, right? There's my r. And then I also have to have the 3 slots for my dividers. Remember, the number of slots that I've got is equal to n minus 1. That gives me r plus n minus 1, total number of places that I can put 3 elements. For example, let's say that I don't roll any 1s. So I get my blank spot there. And then I roll 2 2s, so the next one is my blank spot. And then I don't roll any 3s. I roll a 4, and there you go. There's the combination that would represent 2 2s and a 4, all right? So this becomes r plus n minus 1 C r, all right? So I'm pulling r out of r plus n minus 1. Well, r plus n is 7 minus 1, that's 6. Choose 3, all right? So 6 choose 3. 6 choose 3 is just 6 factorial divided by 6 minus 3 factorial, right? And then we pull out the orders by dividing also by 3 factorial. So this becomes 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. And then 6 minus 3 is also 3, so it's 3 times 2 times 1 again. And so our 3, 2, 1, those cancel out there. Our 3 and our 2 together cancel out the 6, and we're left with just 5 times 4, which is 20. So there are 20 ways that rolling 3 four-sided dice could come up. So what about my smoothie? Well, I've got this little smoothie maker. It doesn't hold a lot, but you put it down on a little blender thing and it blends up smoothies. And let's say that in a year, I want to open up a smoothie stand. And I've got some fruits that I'd like to use in each one of my smoothies. How about strawberry? We could put banana, mango, kiwi, blueberry. How about orange slices? What else? That probably looks like enough. Maybe we'll add pineapple to this. All right. So I've got n equal to 7. And what I want to do is I've got this plan to go through every possible combination and ratio of these guys from here until a year. And I want to know, and I've got this ranking system. I've got, does it, how's taste in terms of cost, because some of the fruits cost a little bit more than others, ability to hold form, does it have a good consistency? I've got this whole rating system. And so what I'd like to do is, like, once a day, have a smoothie, rank it, and then by the time a year has passed, I should have an idea of all of my favorite, maybe the top 10 favorite, so I can create my menu. Now, my smoothie thing maker is not all that big, so I can only put a selection of 5 measures of each one of these in. So I could put a measure of strawberry, 2 measures of blueberry, a measure of pineapple, and a measure of orange slices. That's 3, or 4, and one more measure of pineapple. And I'll just go through every possible combination. How long is it going to take me to do that? Well, if I use, there's no order, because once you put it in that blender, it's completely mixed up. No order whatsoever. So, and I could have duplicates. I could make an entire one of nothing but kiwi. Please put in the comments section if you think these are a bad selection. I have no idea. I don't drink smoothies, to be honest with you. Anyway, what we've got is 7 plus 5 minus 1, choose 5 using our system, okay? Now, so this is 7 plus 5, that's 12, minus 1, that's 11. So this is 11, choose 5. 11 choose 5 is equal to 11 factorial divided by, well, we're going to start out 11 minus 5 factorial, and that is going to take out the ones that we don't pick for that particular run. And then we're also going to have divide by 5 factorial in order to pull out any of the order whenever we do finally select 5. And so this is going to give me 11 times 10 times 9 times 8 times 7. This guy right here is equal to 6 factorial. So when you divide 6 factorial into 11 factorial, you're left with 11 times 10 times 9 times 8 times 7. And then we're going to divide by 5 factorial. And so this is going to give us, well, actually 5 we can take out of, what do we have, 5 factorial? 5 factorial is just equal to 5 times 4 times 3 times 2 times 1. Let's see, the 5 and the 2 can cancel out the 10. I can take a 4 out of 8 and get 2. I can take a 3 out of 9 and get 3. And so really what I've got is 11 times 3 times 2 times 7, which is equal to 462. Wow, I better get started drinking soon, huh? So there you have it. Enumerating and counting the possibilities by hand, especially for large values of n or r, can be darn near impossible. But we have all these expressions. We've got n to the r, we've got npr, we've got n choose r, we've got n plus r minus 1 choose r. Now you know how to apply them.